Hi everyone, I'm Shobhan, a PhD student at UIUC, and I will be talking about our work on potential field-based metric learning. Deep metric learning is defined as the problem of learning a representation space where semantic similarity between image embeddings is encoded as distance. Moving on to past work in metric learning, we can categorize all current methods into two broad categories, tuple-based and proxy-based methods. Tuple-based methods rely on first sampling a set of embeddings from the mini-batch with a pair of examples from the same class, while the rest being from other classes. They enforce same class examples to be closer to each other than to samples belonging to other classes. Examples of this kind of loss include the triplet, contrastive, and n-tuplet losses. On the other hand, proxy-based methods rely on moving samples of each class towards hypothesized class centers called proxies. Examples include the proxy NCA and proxy anchor losses. Tuple-based losses have two main disadvantages. First, they need computationally complex sample mining strategies to work. Second, while moving the embeddings, they disregard the overall structure of the representation space, modeling only a subset of interactions. To see how this can lead to reduced feature quality, consider that these five embeddings were sampled in a tuple. In such a case, the blue class embeddings would be moved in the direction shown by the arrow towards the red class embeddings that were not sampled in the current tuple, leading to suboptimal features. Proxy-based methods, on the other hand, do not model sample-sample interactions at all, losing rich supervision that could have been gained. So the question we try to answer is, can we better model interactions between the whole embedding space? Our method, PFML, proposes a way to do so by using a continuous potential field to model interactions between samples. The use of a potential field to efficiently model interactions is motivated by physics and by its previous successful uses in modeling interactions in fields like robot path planning. In PFML, each image embedding exerts two fields, an attractive potential field towards same class examples and a repulsive potential field towards different class examples. This encourages intra-class clustering and inter-class separation in the learned representation space. The net force on a point is calculated using the class potential field, which is the superposition of all such individual fields acting on embeddings of that class. Specifically, the force applied is equal to the gradient of the class potential field at that point. The design of the individual potential fields in PFML brings about a major change in comparison with all other DML works. In PFML, the force exerted, which is given by the gradient of the individual potential, decreases with increase in distance, as opposed to past methods where it either remains the same or even increases with distance. This helps learning in the presence of annotation or label noise or on datasets where there are large intra-class variations. This property also helps ensure that superposition of potentials still yields local extremum near embeddings, which we theoretically prove in proposition 1 and corollary 1 of the supplement. The individual potentials also limit attraction and repulsion to beyond and within delta distance respectively to avoid unnecessary interclass separation. PFML also uses proxies to augment the field generated by embeddings. Proxies generate their own field and are affected by the class potential, just like embeddings. During training, force is applied by optimizing network parameters to minimize the total potential energy of all embeddings and proxies. To summarize, PFML first calculates individual attraction and repulsion fields belonging to embeddings of all images in the batch and of proxies. These are then superposed to calculate the class potential fields for each class. The class potential fields are then used to calculate total potential energy, which is minimized by updating neural network backbone parameters. Things learned by PFML are empirically validated on three standard zero-shot image retrieval benchmarks commonly used to evaluate DML methods. The first being the CARS 196 dataset, second being the CUB200 BIRDS dataset, and the third being the Stanford Online Products dataset. It shows state-of-the-art performance on all three datasets, significantly outperforming all current methods. We evaluate PFML using four standardized backbones: testnet, Inception, VIT, and Dino, with PFML consistently outperforming all other methods whenever using these backbones. We also evaluate PFML and other DML strategies in the presence of 20% label noise, where PFML hugely outperforms all previous methods by more than 6% in terms of recall at 1. We attribute PFML's robustness to label noise to two main factors. The first being its decaying with distance interaction strength, and the second being its modeling of all interactions without discarding any. We also study the effect of varying different parameters of our method. We find that increasing the number of proxies improves performance up to a point before it saturates. The radius parameter delta, on the other hand, did not significantly affect performance in our experiments. We also find that a higher rate of decay of interaction strength with distance improves performance over a milder decay. Additionally, extending repulsion to beyond the delta radius harms performance, validating our design of limiting both attraction and repulsion to within the delta radius. To summarize, our PFML approach introduces a novel continuous potential field designed to capture all sample interactions. A key feature is its decaying with distance influence model, which significantly boosts robustness to label noise and enhances proxy alignment with training data, which both lead to improved performance. Ultimately, this allows PFML to achieve state-of-the-art performance in zero-shot image retrieval, in both cases the presence and absence of label noise.